All right. Here we go. Kinematics. Oh. No wonder I'm not getting many questions. I have to write my number. Okay. So what we're describing in kinematics is 2D motion. Motion. Okay. So keeping up with x and y. That's really all it is. My transitions are so effective, everybody feels like, okay, we got to reset. We're done with vectors. So that's all it is. It's doing the exact same thing you did before. X equals xi plus vit plus 1/2 at squared. Now we also have y equals yi plus vyt plus 1/2 yat squared, whatever. Okay, it's the same kinematics. We just got to do it both ways. All right, that's really all it is. But then how to do that in the math, it gets complicated. So let's start by thinking about a mass on a frictionless surface. Okay, and we're going to say that a vector equals 0. So what does that mean? If a vector equals 0, what is ax? 0. What is ay? 0. So this is uniform motion, constant or no zero acceleration. Okay, so remember we just talked about it. Ax equals 0, ay equals 0. Uniform motion. Okay. So we're going to draw a trajectory. Shouldn't the graph reflect on the opposite side of the y? Did I mess that up? Probably not. Okay, I might have. Let's see. I don't have time to look at it. Let's draw a trajectory now. Okay, new kind of graph. It didn't make it onto that list. But now I'm going to draw a trajectory. And that means this is not a kinematics plot. This is actually what something did in space. X and y. So here x and y means the x-axis and the y-axis in space. Okay, how am I going to represent time on this drawing? I'm not. Okay, if this was like a class with the stupid animations, I could make something move, but it's not. Okay, it's a regular class with chalk. So I'm going to draw one here, and it's dotted. And you know what dotted means? It used to be there. Okay, it's not there anymore. And then I'm going to draw like a line like this, and I'm going to draw it solid there. And that means now it's there. Right? It moved from one place to the other. Okay, because I can't make it move. Okay, so what we want to do is describe that motion. Okay, let's see. So let's put some bullets here. So one is, let's think about some vectors. R naught. Can you guess what R naught might be? So R in general is the position vector. Okay, it doesn't mean radius when you get into higher level physics. R means position. So R naught means the initial position. So if I had to draw the initial position vector on here, I would have to draw it from the origin. I have no choice. Must start at the origin like that. R naught. Okay? But now I may also want to draw the velocity vector. So let me write that. R naught, initial position. Now, what if I wanted to write it in vector notation? Oh my God. Can you handle this? X naught I hat plus Y naught J hat. Right? You're used to having an initial X and an initial Y. Let's put them with unit vectors and call it a vector. Look at that. So there's X naught, and here's Y naught. So there's that unit vector becoming useful again. Now I meant to draw this dotted. Let me go back with your pen and make that dotted. Let's see. That's the path. So now we want to draw, say, the velocity vector. Okay? So we know it's a constant velocity because we know it's not accelerating. So here, I'll just draw it here where it was. We'll draw it like that. And we know it's along the path like that. So you could draw it there. All right? But you might say, wait a minute, but I could also, okay, so this is like this. V, it's got an X component. It's got a Y component. Maybe you can kind of see that, right? It's got some Vx here and some Vy there. That's a little weird, right? Because here I drew them on the coordinates and here I didn't. And you might also say, you know, I didn't want to put it there. You should have put it here. You're living in the past putting it here. You need to live in the present and put it here. Okay? But why can I put it either here or here? When is it that you can move a vector around and when can you not move a vector around? You can almost always move a vector around. Okay? The reason I can move velocity, not position, is the position vector is in a coordinate system, and we always draw a spatial coordinate system. Right? Almost every problem, you're drawing x, y for a trajectory as the x position and the y position. Therefore, when you draw the position vector r, you really do have to put it at the origin for it to be the real position vector r. When I draw the velocity, this is not a velocity coordinate system. If you wanted to, you could draw a velocity coordinate system, and then you're doing solid-state physics. So don't do that. Okay? Don't bother to draw a velocity coordinate system. Just put the velocity vector where it kind of makes sense when you're thinking about the problem. And then if you really want to see the components, draw yourself a little baby coordinate system. Oh, there's Vx and there's Vy. See, I kind of drew a little velocity coordinate system. I can put it anywhere I want. Because the origin of the velocity coordinate system doesn't care about the origin of the spatial coordinate system. They're different coordinate systems. Why would they care? It's like an alternate universe. Okay? So that's why when you do problems, you'll put velocity vectors anywhere. You'll put acceleration vectors anywhere. You'll put force vectors anywhere. But the position vector is the one that you actually have to think about where the origin is. Okay? So we could describe this one this way. We could say, okay, that's moving there. That's moving there. Another thing about 2D motion is that the x and y motion are independent. In this case, motion are, x, y motions, I'll say motions are independent for now. Okay? So some people take this too far, and they think it's a law of the universe that x and y motion is uncoupled and independent. That is not true at all. All the problems you do that make sense, it's independent, right? When I throw something in the air, x and y are not coupled and independent. Right? It just moves along in x, there's no forces in x, there's one force in y, they're independent. But say circular motion on a string, you know how they just give you the formula for that and they don't derive it? That's because it's coupled and really hard. Okay? So x and y is not always independent, but in this case, we'll tell you when it is, and in this case it is. It's just something floating on a table. So there's no forces, there's no hill or anything like that. Okay? So the way you would solve this, the way you would work on this problem, if this were a problem, it's just an idea. Let's see. So if you wanted to do it, mess with it, you'd say apply A equals 0 kinematics, right? Uniform motion kinematics. If this were a problem and you were given initial values and you were asked where is it going to be, so let's think how you would do this. Like if you're not fully down with vectors, if you say, I don't want to deal with vectors, you'd say, I'm just going to do the x and y motion separate because you said they're independent. And you can do that. You can say for A equals 0, how do I describe the position? X equals x initial plus Vxt. Well, you're really just using the components we gave you, right? So x naught, I called it naught because I'm old, right? X naught plus Vx, that was the component here. And you say, okay, I can't do vectors. I'm just going to call this y. Y equals y naught plus Vyt. You can do the whole problem that way. You don't have to write it as a vector if you don't want to. Sometimes, though, a problem's a little easier if you write this. What if we wanted to take everything about the x? We'd put it in here. X naught plus Vxt I hat. Look at that. You can put the kinematics in parentheses and just call it I hat. Plus y naught plus Vyt j hat. I dare you to do that once. Okay, it means the exact same thing. Okay? All we're saying is the position will follow these coordinates around. So therefore, this is the position vector. Okay. Does anybody feel super bold? If you feel super bold, I dare you to do this. Oh my God, look at that. Who would ever do that? Right, what does that mean? What is it? It's the full vector notation. R, the position vector R, is the original position vector R naught plus Vt. It's mathematically identical to this. Right? It's x naught plus y naught, x naught I hat plus y naught j hat plus Vxt I hat plus Vyt j hat. And it's just regrouping them from here. See, same thing. This is how like grown-up physics books would do it. It's not how I do it. Okay? So I would recommend you always want to start here. Think about this. Sometimes this helps. Sometimes, not always. Okay? Let's see. Now, so that we're not going to do that problem, but another thing to think about is identify vectors in kinematics problems. We sort of did that. We drew R naught, we drew V's. We didn't draw any acceleration vectors yet, because acceleration was 0. We'll do it in a minute. One thing we want to do is take these concepts and go back to our graphs, right? So on the homework, one of the problems says, draw the x versus time and y versus time position graphs for this motion. So that's what you got to do. It's multiple choice, right? You don't have to actually draw it, unfortunately. But let's just think about it. I'll get you started, right? I'll get you started. So it looks something like this. Remember, that is x versus y, but now we're talking x versus time and y versus time. Where does it even start? Right? You got to think, where is it going to start and what's the slope going to be? And are the slopes the same? Think about how it's moving. Is it moving faster in the y or faster in the x? I don't know. And does it start, do they both start here? No, they don't start there. That's the origin. Does it start at the origin? No, it doesn't. It starts kind of high on the y, yeah, and kind of low on the x, doesn't it? And then as it evolves, they're going at different speeds, right? So this is a case where you've got to think about a physical actual trajectory on a plane. Think of it as uniform motion along that line and see if you can turn that into kinematics graphs. Or see if you can get, you got a 50% chance, right? There's 4 sets and you get 2 guesses. So. But you're going to do it with your brain, I know. Okay, so this was 2D motion, 0 acceleration.